Hi, everybody. This is Aaron Murakami, and this is March 18th, 2015. And on the line, we have Eric Dollard. Coming up here on the 22nd of March, we're going to be launching Versor Algebra as applied to polyphase power systems. And this is a pretty in-depth book on a math system that's necessary for the true analysis of pretty much any type of phase power systems as developed by Tesla. And we're going to kind of go over some of the key points that's in this book. Can you hear me okay, Eric?
Yeah.
Okay. So basically, a lot of people who've been following your work are familiar with some of the old Borderland papers going into the symbolic representation of some different topics like the Four Quadrant theory that I think was probably most people's first introduction to that concept. And fast forwarding to 2012, a couple years ago, you gave a talk at the Energy Science and Technology Conference, which was the Four Quadrant representation of electricity. And that presentation was about 4.5 hours long or so. And then shortly after, we released a book that went into a lot of the topics that you didn't really have time to go into at the conference. Plus, it included some of the math. And that was basically your attempt to simplify the Four Quadrant concepts so that the layman could understand it, because you used a lot of very simple analogies such as moon phases and where the hands are on a clock depending on what time it is and things like that. And so basically where a lot of this Four Quadrant math came from and what got you into it was the son of Philo Farnsworth, who's the inventor of the television. He was a friend of yours in Bolinas, California. You actually lived with him, and do you want to kind of go into the story of how that relationship developed and how the inspiration for this type of math came about?
Well, it seemed quite important to Philo that I pursue this Versor Algebra subject, particularly as it pertained to hyperbolic functions, and he gave me a book that belonged to his father that was called Physics and Mathematics and Electrical Communications, and that kind of got me started in all this. And at the same time, I had begun reading Steinmetz's Theory and Calculation of Alternating Current Phenomena, and then it pretty much became a lifelong pursuit to study this field.
Mm-hmm. And so this upcoming book coming out on March 22nd is Versor Algebra as applied to polyphase power systems, and that essentially could be considered part 2 to Four Quadrant representation of electricity. Is that right?
Exactly. It's an extension.
And so basically the Versor Algebra book is, as you mentioned, an extension to the theory of imaginary numbers, and basically you're taking it deeper and farther than anyone has really taken the concept of imaginary numbers before.
As far as I know, yes.
And of course, I don't have a mathematics background myself, and so it took, a little bit of time to kind of look into the kind of the descriptions that you gave. You do give very simple explanations in common English, and so even if somebody isn't really deep into the math, at least from a historical standpoint, it's pretty fascinating what the real story is and what electrical engineers are using today to analyze these systems and to be able to see really how it's lacking. So basically this book provides the theoretical basis which has been lacking in any of the major books on the subject. Do you want to kind of go into that?
No one's ever really, in the few textbooks that are available on the subject in the original paper, the theoretical basis has never really been developed. What should be a whole book, like the book we're talking about, was only left a couple of pages, which never really made the step in the reader's mind.
Mm-hmm.
And I think actually the writers themselves did not understand the connection.
Mm-hmm. So now Tesla, as we talked about in the past, is that he really didn't have a theoretical basis for much of any of his work. He just kind of was intuitively guided and kind of had a good sense on things, but did not really have like a mathematical basis for what he was doing for pretty much any of his work, and especially with the Polyphase Systems. And then eventually General Electric basically hired Charles Proteus Steinmetz, who was kind of tasked with basically breaking Tesla's polyphase patents, right? Because
to some
they wanted
extent,
in on the
yeah,
action.
and coming up with the theoretical basis for alternating current that could be used by all engineers.
Mm-hmm.
Something that Tesla did not do.
Okay. And so Steinmetz, so his method was basically based on Pythagoras and Descartes' coordinate system. Do you want to kind of maybe give a description of what the Pythagoras method is and what the Descartes method is?
Well, the Pythagoras system is a form of addition that's no longer in a straight line, but it's in a right triangle. So in direct current, you can add 1 volt and 1 volt and get 2 volt. But in the Pythagorean system, 1 volt plus 1 volt equals the square root of 2 volts. And that's a situation that can occur quite often in electrical engineering. The Descartes method is similar, is based on a right triangle and being able to find by a system of coordinates any point on a plane by defining it in what are called Cartesian coordinates, and then that gave the concept of latitude and longitude. And of course is also very important in alternating current theory, because then you can identify your position on a cycle, or you can identify the vectorial result, as by the Pythagorean method, of the resulting voltages or currents in an angular system.
And so, but a lot of this work that Steinmetz was involved with developing for his analysis mostly just applied to the alternating current electricity itself, but it really didn't apply to the rotating electric waves?
No, no one had been able to take it that far yet.
But with the rotating electric waves not being accounted for in Steinmetz's work, but he did start to lay a theoretical foundation for it, but never really expanded on it?
It was just something that would appear in the appendix. He pointed out that the square root of -1 is actually one of 4 roots in the equation of, or the mathematical expression of 1 to the 1/4 power. And then those gave you the 4 positions in a cycle, and that led to the Versor expression and the developments and what have you that I gave in the 4 Quadrant theory lecture.
Mm-hmm.
That carried that root concept even further.
Mm-hmm.
But Steinmetz never carried that into the polyphase power system because he felt content in what he was able to calculate, and also in his later years, Steinmetz became kind of petrified in his own theoretical basis and was not really interested in carrying anything much farther.
Mm-hmm. So with the rotating electric waves, if his math was mostly adapted for alternating current but not rotating electric waves, you mentioned before that there's 3 types of waves. You have the transverse, which is like the side-to-side, longitudinal, which is like a forward and back, and then there's the torsional wave.
Right, it's a circular wave, it turns.
Mm-hmm.
So this 3rd type of wave is the basis for the polyphase power system.
Because it's like a rotating magnetic vortex that's actually going around the lines.
Right. So the distinction between an alternating system and a rotating system is the power or the magnitude in an alternating system pulsates. It's not constant. So for the positive half cycle, there's a half cycle of energy, and then for the negative half cycle, there's another half cycle of energy, but it's positive, so it's doubled on itself. It's not continuous, but the power pulsates. So if you have a light bulb that's running on 10 cycle per second alternating current, you will see the light bulb flash, but the negative half of the wave lights the light bulb, and then the positive half of the wave lights the light bulb, but lights them both to the same intensity, so the light will be flashing at 20 cycles a second. Now with the rotating system, when one cycle is diminishing, the other cycle is maximizing, so there's always a constant flow of power in a polyphase system. So if you have 3 light bulbs connected to 3 phases, then what happens is the net output of the light will be constant. When one light's dimming, the other 2 will be brightening up, or vice versa. It will go around in a cycle, and while the individual bulbs will appear to be changing intensity, the illumination in the room will be constant. That basically expresses the difference between an alternating current system and a rotating current system.
So at the industrial level, in a lot of shops with big motors and stuff, they have like 3-phase power, and is that one of the primary points or needs for the 3-phase is to keep that power steady instead of it pulsating like a single?
Well, it has to be rotating power. In order to get a motor to rotate, you have to have a rotating force, not an alternating or a pulsating force, in which case the rotor would not turn. It would just hum, locked in one position. This is what Tesla overcame, is they could not make alternating current motors because there was no motive force to make them turn, only to pull the rotor back and forth. So Tesla came up with the system where you had 2 different phases, where when one phase was weakening, the other one was strengthening, and placed them at right angles to each other, and that would cause the rotor of the motor to move in this so-called magnetic vortex, where there's a virtual magnetic pole that moves around inside the motor, whose Versor position depends on the relative magnitude of the phases.
So with the rotating electric wave, I know with when four-quadrant representation of electricity came out, there was little description about this like rotating magnetic vortex going around the power lines, sort of, and it was kind of explained like almost like a magnetic drive shaft, which goes from the power source rotating around the lines, and when that gets to the polyphase motor, then that rotating magnetic vortex imparts the push in the motor itself?
Yeah, the rotor of the motor is held captive by the magnetic vortex and locked into that position, so it turns in synchronism with it. In common motors called the induction motor, it has to slightly fall behind and lag with a certain beat frequency so the rotor can extract its power from the field to produce the magnetism to lock into it. So a synchronous motor will lock right into the vortex, where an induction motor has to fall behind so that there can be a small amount of power generated inside the rotor to make it spin, where in the synchronous motor, the rotor power is derived externally from a direct current source.
Yeah,
otherwise, both are held captive to some extent by the rotating magnetic vortex.
Now, the rotating magnetic vortex going from the power source around the lines and into the motor, I mean, that right there is kind of a fascinating concept, that it is like a big magnetic drive shaft, so to speak. Is that concept like commonly understood in electrical engineering?
No, most of the basics are no longer understood in electrical engineering. These things are all pretty much forgotten, and it's all just thought of abstractly, and it's pretty much thought of in alternating and not rotating terms.
Mm-hmm. So now with Steinmetz developing the math, which mostly applied to AC and not the rotating electric waves, in some of your notes you mentioned that Steinmetz never really made a distinction between a vector and a versor.
No, they kind of merge together. He doesn't show how the two parts work separately.
Okay, can you give like a simple description of like each one, how they're different and how he kind of mixes them together?
Well, a vector is something that has a length and a position, where a versor is just a position. Mm-hmm. So with the versor, the position is expressed by the versor, and then the magnitude, or what's called the tensor part, is put onto it later, or you can use a multiplicity of versors, which then combine into a vectorial direction. In other words, you have a magnitude and you have a position.
But like with the hands on the clock, that...
Well, let's say we can take the clock, okay? So a clock is a Versor apparatus. It gives position. And the numbers on the clock basically represent versors, 1, 2, 3, 4 around. Those are versor positions. In a certain sense, they're imaginary numbers in that they don't indicate a quantity, they indicate a position. So the numbers on the clock are imaginary numbers, and the vector, which is the hand on the clock, never changes length, so it's a unit value, so it drops out. Now, of course, you have two hands of differing length. You have the hour hand and you have the minute hand. Now, you can take the two of those and deal with them as vectors and then combine them into a resultant. But that serves no purpose on the clock because you're simply after the angular positions. And on the clock, you have two sets of angular positions. You have one for the minutes and you have one for the hours and then possibly a third one for the seconds. And there's no reason to combine those vectorially. And the lengths of the hands don't matter other than just that they identify that one is hours and minutes.
So
the daylight savings time is an example of a Versor operation in that you perform a Versor operation of adding or subtracting 1 hour. In other words, you multiply by one imaginary unit, one step forward or one step back, and then that gives you either real or imaginary time. So right now we're operating what's called imaginary time, and then standard time will be called real time. So multiplying by one Versor step, that one Versor step being what's called an imaginary number, transforms you from one system of rotation to the other, which are displaced in phase. And that's exactly how a polyphase system works. It sets up a sequence of those, and that's what causes the rotation.
So this mixing of the vectors and versors that Steinmetz is doing, that is still kind of confused in this day and age, right, as far as analysis on polyphase power systems?
Yeah, it makes it harder to understand the Fortescue method and the symmetrical coordinate systems and all the various type of polyphase mathematics because the vectors tend to complicate the stuff. The whole reason for the use of the symmetrical coordinate system is the vectors are basically eliminated and you end up with a multiplicity of Versor systems which then are recombined into a vector system. So the vector system is basically dismantled into a set of Versor systems where the vectors all are of unit value, even though each system, like the hour hand and the minute hand, might have different values within each system. They're consistent. In other words, the hands are the same size. They don't change as they go around. But then after you do the Versor operation, such as converting the daylight savings time, then you go back and take your various components or your coordinate systems and recombine them, and that gives you the resultant vectors. That's basically how the system of symmetrical coordinates, or what's in engineering called the system of symmetrical components, operates.
So originally, Oliver Heaviside hinted that the vectors and versors actually should not be mixed, but he didn't elaborate on it too much.
Well, Heaviside was the one that basically established the whole vector idea to begin with. Okay. So the vector concept is actually fairly recent. It's a somewhat modern system of mathematics, considering going back to antiquity and, in the Middle Ages and all that. And Heaviside was the champion of that. But Heaviside did not think in terms of versors, and particularly because versors came out of what was called the quaternion system of mathematics, which was a complete mess and did not really provide much of any type of useful result. So Heaviside dumped that and switched to his system of vector calculus, and then that kind of resulted in the overall abandonment of quaternions. But nevertheless, the Versor system, which could be viewed as a type of quaternion system, is actually very important for alternating current study.
So now it was, is it Alexander McFarland who basically developed the turn imaginary number system into Versor Algebra, or is he the inventor of Versor Algebra, McFarland?
Well, I wouldn't say he's the inventor, but you might say that he was the champion of that particular branch of mathematics and carried it to a level that no one else had ever done, including Versor expressions for hyperbolic functions, which was the thing that Philo Farnsworth wanted me to pursue, and that's why I went into the work of Alexander McFarland, because he was the only writer on the subject.
And so
then I turned around and applied that to the Steinmetz method in the alternating current book, and then out of that emerged the Four Quadrant theory. And the two papers I wrote when I was living on the street in San Francisco, the symbolic representation papers, which about a decade later were put into the public by Borderland.
Okay. So you basically extended McFarland's system, and that led into the development of all the Four Quadrant.
Well, I wouldn't say I extended McFarland's system because it's very deep, and the possibilities are almost unknown. It's a very involved system. I took the necessary components of it that were necessary to apply it to alternating current theory.
Mm-hmm. So now with talking about the polyphase systems, the whole concept on the symmetrical coordinates developed by Fortescue, that made it possible to analyze any number of multi-phase systems, and you're saying that this mathematical method, for example, is not only can be used on polyphase systems, power systems, but can also be used to analyze music and other systems?
Well, anything that follows that line of reasoning, so you can have a polyphase power system, you could have polyphonic music, and even the numerological understandings of Pythagoras enter into the situation. So it starts to become very foundational, both for the foundations of electricity and music and number theory in general. So the possibilities are very interesting, but because Fortescue was an engineer and not a mathematician, that's completely ignored by academia and mathematics, who usually have a disregard for the work of engineers. But the engineers do have the complication that they have to be right, and that if the theory doesn't work, you don't get paid. Mm-hmm. Where the mathematicians can just keep cranking out more theories, and the funding lasts indefinitely.
Now with Bach, for example, his music is polyphase music, so you're saying there's like multiple lines of music that are played simultaneously on top of each other?
Yeah, Bach's music is an excellent example of sequence mathematics. So you'll have a melody, which is a sequence of, typically 4 notes, and they will go through their Pythagorean pattern. They'll be in series. They won't be in parallel. But then that same melody will drop down to another octave, a lower octave or a higher octave possibly, and it'll be the same melody, but it will be time delayed from the original melody, and the two melodies interact to produce a harmony, and you will have, in general, 3 or 4 of these so-called phases moving, which is very similar to the Tesla rotating system, where one phase is a delayed equivalent of the one that preceded it, or a leading equivalent of the one that will follow it. Bach's music does the same thing. It's what's called polyphony, where more than one note is sounded simultaneously. Just like in Tesla's system, more than one alternating current is produced simultaneously.
So with the big church organ playing the music, bouncing off the walls, you have it coming from the organ, but then you have like a time-delayed echo that kind of overlaps.
Well, that would be the origins of the polyphonic process, because it's actually musically polyphony didn't come about until the early Renaissance time, after the Middle Ages, and it would be a natural consequence of if any music was being performed in a church, is the echo of the church would cause the melody of that music to come back at a later time. And then the organ itself is inherently a polyphonic instrument because more than one note can be sounded simultaneously. So out of the church sprang the music known as polyphony.
Okay, so there's you're mentioning that normally it's very difficult to solve equations higher than the second degree, but with the Fortescue method of symmetrical coordinates, it does make it possible. So can you kind of explain what a first degree would be, second degree, and what it means to go beyond that?
Okay, so if I have the equation that that x minus 1 equals 0, that has one root. If I have the equation x squared minus 1 equals 0, well, now that has two roots. Now, the first order equation, x equals minus 1, or x equals plus 1, or x minus 1 equals 0, or whatever type of, there's x to the first power, that's an arithmetical process. If it's to the second power, then you have to involve a type of analog computer mechanism known as the quadratic equation, which is a mathematical process at which you will arrive at the two roots. With the third order equation, there is no such process, and it has to all be done experimentally. And you'll have three roots, and they'll be very hard to get at. A fourth order equation, you'll have four roots, and so on up the line. And the more roots you have, the harder it is to arrive at them. And basically, in the system of algebra, there are no roots available for equations higher to the second degree. Now, when you have a three-phase or four-phase power system, those represent equations to the third and fourth degree. Is now you have a dilemma as to how to come up with solutions to those equations, and that is the purpose of the Fortescue method. So the Fortescue method would have possibly applications in theoretical mathematics to come up with solutions to higher order equations. And apparently it has been used for that in the references in the textbooks on the subject, but the textbooks themselves are written for engineers and they don't discuss that aspect. But when you're dealing with an equation for like a transformer winding or waveguides or anything where you have so-called multiple degrees of freedom, they very typically end up being fourth order equations, and trying to come up with a general equation and its solutions for a transformer winding is basically an impossible mathematical task as mathematics is commonly understood.
And so your book, Versor Algebra as Applied to Polyphase Power Systems, is you're presenting basically the first theoretical basis for what this Fortescue method is that allows the analysis of any multi-phase systems, and you simplified it.
Yeah, it's the theoretical basis which has never been provided whatsoever, extending the theory of imaginary numbers as it was first done in the Four Quadrant theory presentation, and then this takes it into a general theory, deriving it from your basic exponential functions and extending the ideas of sines and cosines and such things into more complicated systems. And then once that basis is established, then I go into a general system for any number of phases and come up with the Pythagorean number relationship that works for any number of phases, and then pretty much leave it at that point. And then the part that will be coming out later that follows then takes this mathematics and applies it to representing any number of phases individually from one phase to 9 phase. It's quite an ordeal. And then showing how it all breaks down into this system of sequence algebra, where there's a number of rotations going on at different rates within these polyphase systems. The fascinating thing about the Fortescue method is it showed that there's all these rotational and alternating waves that exist in power systems that were never before recognized until the advent of this method.
So, like, what's an example of how you simplified it? Because you've basically made this whole process simpler than it's ever been, and you're able to do this without
the complication in the two books on the subject are, for one thing, are typo errors, which always seem to work their way in, and all it takes is one plus in the place of a minus, and it's hopeless. So you end up having to rederive everything yourself, and it's confusing. The other complication is one of these quarks in theory that Steinmetz and Heaviside constantly railed against, but they got it anyway, was the decision to standardize on counterclockwise rotation, which puts a negative sign in all of your exponents, which further confuses the situation, and then to attempt to express it in what are termed phasors, which are rotating vectors and not versors, which cause a whole bunch of inconsistencies. And then on top of that, the same letter is used to symbolize a number of different components, the distinction being made with subscripts, which then you end up with more subscripts than you have, and it all turns into such a mess that you can no longer visualize the process. So using some of Steinmetz's ways of going about it and some of my own contrivances to simplify the thing by using uppercase and lowercase letters and using the Steinmetz method of placing a dot above or below the letter representing the variable instead of a string of subscripts, I managed to simplify it down into a basic algebraic expression that can be visualized at once, and not something that you just had to make sense out of all these subscripts and the fact that the same letter was used 50 times on one page. You couldn't get anywhere with it. So that was part of what I had to go through.
So basically,
it was quite an effort to untangle the mess. It was very difficult to untangle the mess. Not only to provide the theoretical basis as an extension of logarithms and the theory of imaginary numbers, but to get all the backwards, rotations and the phasors and everything else all out of it and get it into a simple form of sequence algebra that could be very easily visualized and worked with.
Now, people who've been following your work are familiar with the concept that's been brought up multiple times, which is the square root of -1. Can you kind of maybe give a simple explanation of what that even means in terms of all this?
The square root of -1 is, as an arithmetical expression, is an impossibility. And that's where the so-called imaginary number concept came about, because it was considered the root. It would have two roots because it's a square root. In other words, it's something to the second order. The complication is if I take a number and I square it, if I take +2 and I square it, it gives me 4. In other words, 2 times 2 is 4, but if I take -2 and I square it, -2 times -2 is also 4. So there can be no such thing as a square root of a negative number from an arithmetical standpoint, but from a geometrical standpoint, that's not necessarily the case. So you can extend that concept to the square root of +1 also has two roots. In other words, you can have -1 times -1, or you can have +1 times +1. And the square root of -1 also has two roots, where the number 1 now is replaced by the letter j, and you can have +j and -j, and these can be combined together into a fourth order equation, or a fourth root of +1, which will give all those roots. And then that basically is the beginning of the sequence algebra, or the Versor Algebra system, is the fourth root. So the square root of -1 historically led to this, but only until McFarland and Steinmetz and Kennelly developed these ideas further was it found that initial case of a more sophisticated system of roots where there is no -1 under the root sign anymore. It's always positive. Mm-hmm. And then that in the system of symmetrical coordinates, that can be taken even further until eventually all phases can be expressed as fractional roots of 1, and you can eliminate the use of imaginary numbers altogether. And it will also describe the movement of all the harmonics of the system at multiple frequencies I have not developed that aspect of it yet. A lot of this stuff takes a long time, and unfortunately, I have many other things to work on, so I can't just keep going on one subject.
Now, there's a statement somewhere, I don't know what book it is, where it came from, but that Steinmetz, General Electric gave Steinmetz permission to create electricity out of the square root of -1.
Yeah, General Electric came out publicly with that statement that Steinmetz was given permission to create electricity out of the square root of -1. There was never any explanation given for it, but it gave the idea that electricity can be created out of an imaginary realm.
Like a different dimension.
Right.
And is that synonymous with the concept of counterspace?
Not directly. But yeah, counterspace is what some people would call another dimension. But as I've pointed out numerous times, there is only one dimension of space. There's no such thing as 3-dimension or 4-dimension space. Those are coordinate systems, such as what we're dealing with in the system of symmetrical coordinates. You don't call each phase a dimension, it's a coordinate.
Mm-hmm.
So there's only one dimension of space, but space and counterspace tend to behave as polar opposites. So the physicist's mind state would tend to call counterspace another dimension.
Right.
Or call the square root of -1 another dimension, but it's not really another dimension. It's a conjugate or complementary aspect of the one dimension that's being dealt with.
I mean, right now you and I are obviously in the same dimension of space, but we're basically at different coordinates.
Right.
In one state, not in another, but it's still the same single dimension of space.
Right.
So now this, after the Versor Algebra is applied to Polyphase Power Systems book, there's another one that'll be coming out after that, and you mentioned it a little bit earlier, but you want to just kind of give a basic little synopsis of what the book is about. It's basically the application of.
Well, it's all part of the same book, but because of the enormity of the project of writing it and getting it published, it's coming out in sections. So the part that's coming out now basically establishes the theoretical basis as an extension of logarithms and imaginary numbers, and then gives the general equations for any number of phases. And then the next section will take this generalized system, which has been established as a sequence algebra, and then apply it specifically to all phases from 1 phase to 9 phases, with a heavy emphasis on 2, 3, and 4 phases. So what we normally call single-phase alternating current is actually not single-phase alternating current. It's 2-phase alternating current because there's a plus and minus. So its expression is the square root of +1. In other words, +1 or -1. It's 2 phases. That's why there's 2 wires. And, of course, 3 phases is 3 phases. The only existence of a 1-phase system, which would be a 1-wire system, is the longitudinal transmission method of Nikola Tesla, where you only have 1 pole in the transformer, you only have 1 wire, and then it's no longer the square root. It's the first root of 1, which is no root of 1 other than 1, so all you have is 1 phase. Mm-hmm. But, of course, that has not been really thought about at all. But I've managed to express the theory of phases to cover its entirety from 1 phase up to 9. The number of coordinates increases with the square of phases, so it becomes, after you get past 5 phase, it starts to become inordinately difficult. Mm-hmm. And what's fascinating is you find with the sequence algebra that there's all these intricate rotations going on within the overall polyphase rotation, where some go backwards, which are called negative sequence, some go forward, which are called positive sequence, some merely alternate, which are called alternate sequences, and then there's skip sequences when you get to higher order systems where some of the rotations occur at more advanced rates than the main waves, so you have certain rotational waves that are going second harmonic and third harmonic and so on. And these are the things that could never be visualized before the advent of the Fortescue method of analysis. These waves, zero sequence, positive sequence, alternating sequence, negative sequence, and advanced sequences were all basically invisible until the math was developed. And then once the math was developed, it was possible to make transformer connections where you could actually put these sequence components on switchboard instruments and measure them, and they actually have a measurable physical reality, but until the mathematics was developed, they were never known about, which is kind of fascinating.
Right. Now, talking about the single-phase system, the longitudinal one, you touched on that in your presentation at last year's conference, which was extraluminal transmission systems of Tesla and Alexanderson, where it's not like going from, where basically self-references. It's a monopolar type system.
Yeah, it's very important, like particularly with my telluric work, because if I'm going to electrostatically receive out of the ground, there's no reference because the ground is now the hot terminal. What am I going to ground to? The moon or Mars? Or it's obviously not practical. So the Tesla system allows for a self-referencing. You could possibly say it grounds to counterspace. In other words, it's within the transformer structure itself that it finds a reference. It's completely in violent opposition to the Einsteinian concept of relativity, where there can't be any absolute point of rest or there's no absolute point of reference. Well, Tesla obviously disproved that with his transmission system, and that he was able to create a one-pole electricity that was self-referencing to some sort of universal absolute ground.
Okay.
He also was capable of doing it mechanically, where he could basically bypass the law of action and reaction and produce a mechanical force that did not produce an equal and opposite reactionary force in the backwards direction. And that's what's known as his geodynamic oscillator. It was capable of producing a unipolar mechanical force that bypassed those laws of Newton of action and reaction.
Known as his earthquake machine? What people...
Yeah. Now, it's not clear that Tesla theoretically understood any of these things. I don't think Tesla realized that he was using monopolar electricity or was developing a monopolar force in the way that we're talking about it, being that he arrived at a lot of this stuff experimentally and through visions. But, of course, because Tesla never wrote anything, we'll never really know the truth of that matter.
So coming up here in the middle of July is the 2015 Energy Science and Technology Conference, and you're going to be doing a presentation which will be including quite a bit of the concepts of sequence algebra or the Versor algebra.
Well, not necessarily, but that will be part of it because there's going to be heavy emphasis on music. So that the presentation is still in the formative phases, so it's hard for me to pinpoint anything specifically. But what I'm going after is basically a continuation of the two previous presentations, where the first presentation dealt more with the mathematical archetype, and then the next presentation dealt more with the process of the ether. The ether is a substance, and the influence of archetypes upon the ether to produce physical manifestation. And now this is going to be taken farther into the combination of those two things to attempt to show how the formative forces and the ether interact to provide us with what's called physical reality. That physical reality or physics is actually not the main part of what's going on, but is more of the residue, the leftover component of a much higher process, which virtually nothing is known about. So I'm sticking my neck out on it, but I'll have something figured out by then.
And that presentation coming up in July is called The Power of Ether as Related to Music and Electricity.
Right.
And that'll be scheduled for being a 3-hour talk, but it could easily turn into 4 or 5 hours.
It's hard to say. I don't know yet. These things, they take their own life. They become their own. Once I get wrapped up into it, it'll probably be quite a bit of material. But then, I've got so many other things going. I'm still in the process of writing the book on the last presentation, which is probably going to be at least 800 pages. So part of that's also ready to go out. But, of course, all of this stuff takes a lot of time. And then, of course, I have my long lines project, which is a lot of work.
Let's see, do you have any final words on the Versor Algebra as applied to polyphase power systems that maybe we didn't touch on? Or because, this is obviously a very important book for anybody who's interested in the so-called Tesla sciences.
Well, basically, it could be an engineering textbook on the subject because this has never been done before. But it's not specifically related to Tesla. It's just that Tesla created a situation that required the development of this mathematics. It's beyond Tesla. And, of course, it's very mathematical by, definition. It's a math book, so for people that are not inclined to mathematics, it might be rather difficult to follow, but for people that are interested in the theory of mathematics and the origin of mathematical theory, specifically in its application to this geometric algebra and geometry and number systems and what have you, I'm sure some people will find it quite fascinating. Anyone that's studying to be an electrical engineer and is right now in the process of learning the system of symmetrical components for analyzing power systems would find this book fascinating and very helpful in that study.
Okay, well, if you're
the other book I'm referring to, which is on the previous lecture, like the previous lecture, will be more descriptive and get into physical types of explanations and practical, actual power line situations and talking about the constitution of the ether. That book is more orientated towards people that are still on the ground level of these subjects. The book is actually called The History, Theory, and Practice of Electrical Transmission. The aim of the book is to first thoroughly prepare the reader to understand transmission in general and apply it to transmission systems that already exist and that are well understood, like telephone lines and power lines and what have you. And then once that's firmly established and the theoretical basis for electric induction and current and all these things is solidly established, then it will be taken into more unusual transmission systems such as those developed by Tesla and Alexanderson and waves and transformer windings and insulators, but it's a very slow sequential process. So the last presentation was kind of a popular overview where I showed a lot of these things but didn't give a lot of details as to about what was going on because it already took 4 hours just to go over the overview. The book will probably take a couple of years to finish, so the part that you have right now is like the first eighth, which is primarily the historical part and some of the basic theory, which I think people will find quite interesting, and it'll make the presentation a lot easier to understand.
Okay. Well, if you're listening to this,
all of these things are actually quite a workload, so with the advent of this people sending me donations of a rather substantial quantity is now I'm able to spend full time working on this stuff and not get distracted with, not having anything to eat or no place to live or my car's taking a crap or somebody's bulldozing my installation or those distractions are pretty much gone now, and I can concentrate my entire effort on these two aspects, the writing of books and the producing of working transmission systems for telluric wave analysis.
So if you're listening to this, make sure to get a copy of this Versor Algebra book. even if it's just to support Eric's work, proceeds from the sales go to Eric and EPD Labs Incorporated, which is the 501c3 nonprofit organization dedicated to Eric's work.
Yeah, I think that's pretty much it. I'd like to point out, the book sales and video sales end of it is what pays the rent and the bills here, and that's waning right now, so that's why more books and more presentations are coming out, but I need to keep that up and going because, right now the input is not enough to sustain the operation here.
Mm-hmm.
So it's going to have to start coming out of my personal funds, which then makes it difficult for me to continue doing the things we were just talking about.
Right.
For example, I have to pay, the gas and food and what have you for people like John Polakowski came out here and spent 5 days here helping me develop the networks that we're going to need on the telluric antenna. But, that's a week that he can't work, and it's a long drive here, and he needs to eat and all that kind of stuff. So the donations that I receive in the mail are pretty much supporting all this, and then the book sales, they pay the rent on the building and the electrical bill and the insurance and all that type of stuff, which actually comes up to a rather hideous quantity every month. So that's where continued book sales are important. And it gives me, more incentive to keep writing.
So thanks, everybody, for listening to this. Make sure to get a copy, and also if you can be so kind as to share it with your friends, share it on Facebook and Twitter. Purchasing a copy of this book is what's going to help support Eric, pay the bills at his lab so he can continue to do this kind of work. And thank you for listening. And Eric, thank you so much for your time.
Yeah, thank you. I'll talk to you later.
Okay, talk later. Okay,
bye.
Okay. Yep, bye.